We got about 1 minute to go, and I do have to tell you guys that I have been grading the exam and then almost done, and then I found out that I had to regrade all of the exams because one of you was very clever to answer some of the questions with exactly the same answers for the first 5 questions. Well, almost all the same answers. And I thought, that's not what it was intended. So I had to kind of go back to change um, the way I grade the first 5 questions. And that's a lot of questions. My spreadsheet right now has, let's see, from column C all the way to column BB are the entries, and some of the entries are calculated. There are maybe about 6 or 7 entries that are actually calculated. The rest I have to put in by hand. So I have to go back and change all of those. All right. So it is time. Yolanda, your mic is on. Just want to let you know. Thank you. All right. So we're gonna get started with today's lecture, and of course, almost 2 weeks ago, we talked about discrete probability. This is the transition from the lotto problem. And if you go back to the class modules, this is where we are. So we talked about counting, so we talked about combinations, permutations. We use the lotto. Is it Super Lotto? No, it's Powerball. So we used the Powerball Lotto game as an example, and then we calculated the chances. We also tried to reverse and figure out, how many tickets were actually sold based on what the lotto statistics is telling us, because we know the probability of winning specific prizes, and since the lotto site has to publish how many people, how many tickets won a particular prize, so we can use that to kind of reverse and calculate the number of tickets that were sold, and that was an attempt to try to model how does the number of tickets sold correlate with the jackpot money. So that was kind of what we talked about 2 weeks ago, because the Wednesday right before the break we talked about the practice exam. So this is a good time to remind all of you that the second exam is on Wednesday, on this particular Wednesday. So if you have any questions about that exam, you can bring it up in today's lecture as well. I'm hoping that you guys got some chance to review the material and just kind of review the material in the sense of trying to make sure that you understand all of the concepts, because the questions are all going to be about problem solving, based on the concepts that we have already talked about. So understanding the concepts to the point where you can apply the knowledge is really kind of important. All right, I'm looking at the text channel of today's date, and there is no traffic whatsoever that I could see. All right. Well, in that case, I'm gonna continue with the lecture. And what we'll be talking about today is this module. Let me just point out where we are now. So we are now at this discrete probability. I'm not going to give you guys any assignment, like the generator assignment is not going to be assigned just yet, because I know you guys are all busy trying to study for the exam on Wednesday. So that's going to be assigned on Wednesday, but not now. Okay, so we will defer that until Wednesday. All right, so let's talk about discrete probability. This is kind of an interesting module because it talks about kind of the same thing that we talked about before, but in a slightly different way, and we also applied what we are learning to solve different types of problems. So what we'll do is, starting from the beginning, I hope you guys also had time to read a little bit ahead, knowing that this is going to be the next module that we'll be talking about today. All right, so module 0305 was the one that we talked about before. So let me just kind of go back to that page so that we know what we are talking about. So this is the counting module that we talked about before the break. And so we're going to reuse some of those terms. The set of all possible outcomes from an experiment is often denoted as omega. So that's kind of what we talked about already. We also turned omega into a function, where we can use it to generate the set of all permutations, coming out of an experiment. So so the term that we are talking about here is what is an event? Okay, an event is basically a subset of omega. Doesn't have to be a proper subset, even though when it is not a proper subset but a subset, then it is not really that meaningful when it comes to the calculation of probabilities. So I want to make sure that you guys are awake. Okay, so if I use E to denote an event, okay, so I'm just hovering over which part I'm talking about. So if I use E to denote an event, we know that E is a subset of omega, but we also know it is not a proper subset of omega. Then what is E? How would you describe E in that case? So I'll give you guys a few moments to think about this, and then I'll tell you the answer. So once again, the question is, E is a subset of omega, but it is not a proper subset of omega. So how would you describe E in this specific case? No, it is not empty. Not necessarily. Nope, it is not a relation, because in order for something to be a relation, it has to be a set of two tuples where each item of a two tuple comes from a set. And in this case, we have no restrictions whatsoever of what E can be. Aha! So I can see Garrett has the right answer. And so does Aiden. Okay, very good. Okay, good job, guys. Yes, so in order, this doesn't have anything to do with tuples. This has to do with what is a set, what is a subset, what is a proper subset. Okay, so so two sets can be, one can be a subset of the other one, but when we say E is a subset of omega, they can be the same thing. But when we say E is a proper subset of omega, then there has to be something in omega that does not exist in E. So in this specific case, since I already said that E is a subset of omega, but it is not a proper subset of omega, that leaves us with only one possibility, which is E and omega are the same. Now, do I know what is in omega? No. Do I know what is in E? I don't know either, but I know they are exactly the same elements. Yep, there we go. So Aiden has the explanation as well in the text channel. So this is the sort of thing that I would like you guys to kind of be able to do, is to not to regurgitate a definition, but to understand the definition enough to apply it. To basically say, oh, okay, we're encountering the same terms that we have talked about before. And since I talk about this and I place this restriction on E, then it is only a logical consequence that E and omega are the same if I claim that E is an event of omega, but it is not a proper subset. That leaves only the possibility that it is the same as omega. All right. So what we'll do is we are going to move on to a particular example of how we are going to apply this. So this is an interesting application of what we have learned up to this point. It does involve permutations, it does involve combinations, but I think most importantly, it has to do with how we look at a problem, how we look at not necessarily the problem, but how we look at a number a quantity that we need to calculate. All right, so let me describe the problem first. Okay, the problem is to ask what are the chances that at least two people in class, a particular class, share the same birthday. It helps to make this more specific. Let the number of students in the class, be n. This is not supposed to be by. I mistyped. It's supposed to be b. Okay, so we're using lowercase n as a symbol to represent the number of people in class. And we want to find out what are the chances, what is the probability that in this class at least two people share the same birthday. So it can be more, okay? It is, I'm including all of the cases like, oh, the first two people share the same birthday, the second two people share a different birthday, and so on and so forth, okay? So how do we solve this problem? Now, in my mind, I'm expecting you guys to go like, okay, I know the answer already because I have read the notes prior to, to the lecture, so I already know the answer, and I just need you to kind of go in and explain it, and I'll be asking questions, along the way. Now, obviously, I know that some of you did not read the module prior to the class, so that's going to be, it's going to make learning a little bit harder. It's also going to, it's just better off, to be able to read ahead of time, and then you can just write down the answers. And Garrett is including a picture. Of course, I can't see what the picture is. Oh, okay. All right, so now we're gonna take a look at this particular problem. And the way we think about this, there are several ways to approach, how do we think a problem like this. The first one is to look at a very small class size. And then we ask basically the same question. Because with a very small class size, we can actually kind of enumerate the cases. Okay, we can actually manually enumerate, all the cases. So that's one thing we can do. And I am just moving things around in OBS because I think my video is covering portions of the screen, so I just have to be careful not to use the bottom part of the screen now for presentation. Alright, so that looks okay. And then we lock preview again. Alright, so getting back to what we want to think about, or how we want to think about this, is to really kind of think about very small cases first. Okay, that's one way to think about it. So what I'm going to do is to use mousepad because it really is just typing stuff, and there's not much need for drawing pictures at this point. Okay, so we think about cases where n equals to 1. Okay. In other words, we have a class of only one person. So when we have a class of only one person, and the question is, what are the chances of at least two people in the class sharing the same birthday? Well, what do you think is the answer? Okay, so we got a bunch of answers of 0. Okay. And the answer is, let me think. Well, let's hold on to this one for a while, okay? So is the answer 0? Okay, we don't know yet. So let's step up to the next one, okay? So we now have a class of 2 people. And in a class of 2 people, what would be the answer to this question? Okay, now with 2 people, it's fairly easy to understand, to calculate, right? So we basically say, the class is a set. It has person A and it has person B. All right. I don't think it's going to be 50%. It's a little bit, let me see, it's going to be a whole lot less than 50%. It's going to be, well, let's work this out. Okay, let's work this out. So in a class of 2. Okay, there are 2 people in class. Okay, so in this case, let's think about omega first. Omega, or let's think about the cardinality of omega first. So we are only concerned about the cardinality, and we can kind of enumerate or list some of the elements in omega later on. But right now we just want to calculate the cardinality of omega. So that boils down to the number of days that can be birth dates of A, and then times the number of the number of possible birth dates for B. Okay. So let me just write it down in English first, and then we'll convert these into numbers. Okay, so the first one is number of dates that A can choose as birth date. Okay, and because B, can use exactly the same number of dates as well, so it's going to be pretty much the same thing. Then you go like, but the question specifically asks about A and B having exactly the same birth date. Yes, I know that is the event that we are talking about. But when you have 2 people in the class, each person can choose any one of the 365-ish days as a birth date. So the cardinality of omega in this case is 365 to the power of 2. All right, so that's omega. Okay, that means depending on the class. Okay, depending on the class, there are 365 times 365 ways for 2 people in the class to have their birth dates. Okay, so that's omega. Okay, that is the set of all the possible outcomes. So are we good with this part? What omega is representing and why it is 365 to the power of 2 when we have only 2 people in class. All right, so, excellent. So now we want to look at E. Okay, so we want to look at, we can also kind of give you an idea. I can give you an idea of what is in omega. Okay, so what is in omega? So I'm using a date, to represent. I'm going to use a 3-tuple to, 2-tuple to represent a birth date, excluding the year. Okay, so we can say, January 1st. Okay, is in omega. Okay, because, actually, I take it back. January 1st and January 1st as a 2-tuple is in omega. So now the question is, why does it look like this? Okay, what are these extra parentheses actually doing? So the innermost pair of parentheses are here to group what is used to represent a date. Now for those of you who say, I don't like this way of representing a date, fine. Use the more typical notation. Okay, you can use a slash to separate the month designation and the day of month designation. Okay, so now it's more clear, right? Because what it boils down to is this is the birth date of A and this is the birth date of B. So using this, we can also have today is the 5th of April, and then we can also have somebody who is born, let's say, 4th of July. Okay, so we have 7-4 in this case. So this is also in omega. So this is just giving you an idea of what elements of omega looks like, when we have a class of 2. It's really just all the possible ways of arranging, dates as birthdays for the 2 people in class. They can be the same, they can be different, and they can also be something like this. Okay, there we go. This is also in omega. Now, this is relating back to something that I observed when grading the exam. I saw some people using 2 elements of the same thing inside the set. That is not a good thing, right? Because when we are not talking about multi-sets in this class. I specifically said that in this class we cannot have duplicate elements in a set. So, well, if that is the case, how come these two are distinct elements? They are distinct elements because each one is a two tuple. So when you compare when you compare two tuples, the values need to be the same at the same position for every single position in order for two tuples to be considered the same. So in this case, because even though we have 4, 5 is the first item, and then 4, 5 is the second item here, and then 7, 4 is the second item here and the first item here, but because the orderings are different, they are as two tuples, they are considered distinct. Okay, so this is also very important to point out. And obviously, if you go all the way to the last one, it's going to be December. And December 31st is the last day of the year. So, that would also be an element in omega. So all of these are elements in omega using a fairly standardized way of representing a date in the year. All right, so do we have any questions about all of this stuff here? Okay, no questions. All right, so now we want to think about E. Okay, so what does E look like? So E is representing a subset of omega where it meets what we are describing here. At least two people in the class have the same birthday or same birth date. Okay, so I should be changing this birthday, which implies that it includes the year, to birth date, which specifically excludes the year from a date. I'm getting irritants in my eyes again, so let me get rid of that. There we go. Hopefully that gets rid of it, because sometimes what that will do is to push the irritant further into the eye, so it becomes impossible to get out. All right, so what does E look like? Well, E is going to be a subset of omega. In other words, elements in E is going to look like elements kind of like this, except it has to meet the requirement that we want, which is at least two people in the class sharing the same birthday. So E is really enumerating all the ways that two people in class can share the same birthday. So what is that going to look like? Well, instead of using this representation, I will just give you an example what it's going to look like. January 1st is in E, because now we have two students or two people in the class having the same birthday. But then we're going to say, but the next day can also be like that. That is also in E. And then the third day of the whole year can also be in E, and all the way to the last day in the year. All right, so cool. That looks pretty easy to work with, right? So now if I ask you in the class of 2, what is the cardinality of E? What would be your answer? To simplify your thinking, you can think about we magically make the Earth revolve around the Sun in exactly 365 days instead of 365.24 blah 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 days. Okay, so you're correct. Okay, so it is 365. So what about the probability? Okay, so if we look at the probability of, basically we use the kind of strange notation of E over omega. Basically it is just saying that when we consider this E and that as omega, as we defined here, it really is just the cardinality of E divided by the cardinality of omega, which is 1 divided by 365. It's like, okay, that's pretty easy to work with, right? Yes? Okay. So now we think about, what about in the class of 3 people? What about that, right? So as it turns out, it gets a little bit harder to figure out, okay, because omega stays about the same. Okay, so the cardinality of omega. Let me ask, see if you guys can think about how what is the cardinality of omega in this case. So I want you guys to think about this a little bit and then type your answer if you want to in the text channel. So what is omega, or the cardinality of omega, when we have 3 people in class? What are all the possible outcomes? So Angel is right, Jack is right. Okay, very good, good job. So it is basically 365 to the power of 3. Okay, that's not too bad. I mean, it looks like we just extend n becomes the power when it comes to the calculation of the cardinality of omega. Okay, that's not hard. Okay, what about e? So we want to know what is in e now. So what is in e? Now it gets a little bit tricky now. Okay, because now we can say 1 1. Okay, 1 1 and 1 2. That is in E now. Let me see what Angel has typed. Chances that 2 students having the same birthday are 3. We are using the same question. We have the same question, which is saying at least 2 people in class share the same birthday. Okay, so it gets a little bit tricky because 1 1 1 1 1 1 is also in E, because we said at least 2, which means 3 is fine too. Okay, you're having everyone in class, of a class of 3 having the same birthday is actually considered, a part of the event set. Then we also have all the quote unquote permutations, right? Because we can have 1 2 1 1 1 1. This is also in E, and then we have 1 1 1 2 and 1 1 in E. These are all examples of elements in E, and we are only looking at a very small, tiny little portion of E at this point. Okay, so we got some questions coming. Let's check out the question. All right. So it's not really quite permutation. It gets even more complicated as n increases, right? Because now we have to think about, oh, so these 2 can have the same birth date, these 2 can have the same birth date, and then these 3 can have the same birth date when we have like 7 people, right? That gets complicated really, really quickly. Oh man, that doesn't seem to be a good way to think about this problem. So now instead of thinking about the problem of we want to calculate the chances of at least 2 people in the class sharing the same birth date, let's invert it, right? So we are basically logically inverting what we are looking for. Okay, so instead now let's figure out the chances that, and then we put a not here, at least 2 people sharing the same birth date. Okay. All right. So in other words, we are just looking at the opposite of what we were originally looking at, because this one turns out to be a whole lot easier to describe and a whole lot easier to calculate. All right, so now we look at the chances of it is not the case that at least 2 people in class share the same birth date. What does that really mean? I mean, can someone put this in a more concise way? Okay, let me just mention what I want to express first, and then you guys can think about how to express it in a more concise and more easier way to understand. So the question is, I want to calculate the chances that it is not the case that at least two people in class share the same birth date. That is what I want to describe, but that's a very clumsy way to do it. is there a better way to describe it? I'm using equal equal here because I want to express the next statement is really expressing the same thing, except it's a whole lot easier to understand. Exactly. All right. Anita is correct. Okay. So this is the same thing as asking the chances that no one shares a birth date with anyone else. Okay. In other words, okay, which is there's another way to describe this too, which is the chances that all birth dates or birth dates of everyone is distinct. Grammar. The birth date of everyone is distinct. Okay, that's okay, yeah. So it does get a little bit more. It's not quite as easy as what Aiden says. But Angel is correct. Okay, so if we use this as our new event, okay, so if f equals to the set of all ways of assigning birth dates with no duplicates, then it is true, what Angel said is true, because omega, or I should say E union with f equals to omega. And obviously E intersect f is an empty set because they can a 3 tuple cannot be in E and F at the same time because they are mutually exclusive. And the way Angel expressed that is also fine. E is basically the same as omega minus F, or F is omega minus E. These are all just different ways to describe exactly the same thing. Okay. Let's see. Okay, we'll get to it, Aiden. I think the answer is actually in the module too, so we're gonna get to it, but we'll get to it step by step. Okay, so if you think about distinct, that's actually pretty easy to work with. We have worked with quote-unquote distinct for a while now, because everything in the set is supposed to be distinct. Okay. Alright, so if we think about f in this case, so f in this very specific case, when n equals to 3, then what kind of elements is going to be in f? Well, we just have to make sure all 3 items are different, right? So 1, 1, 1, 2, 1, 3 is in f, which is the opposite of what we want, right? But so is 1, 2, 1, 1, 1, 3. That is distinct because even though it seems to have exactly the same 3 subtuples, but because each one is, but because the ordering is different, they're considered distinct. Okay, because if you think about why this is distinct, let's just say that we got 3 people in class. Okay, so let's say we have oh, I'm not gonna deal with that. I'm just gonna. I was thinking about using names that reflect people from all different culture, and then I just thought about that and go like, no, yeah, let me just use fictional names that have no cultural references whatsoever. Okay, so we got student X, we got student Y, and we got student Z. Okay, so what these 2 elements in F are really expressing, in the first one, it says student X is born on January 1st. Student Y is born on the 2nd of January, and then student Z is born on the 3rd of January. What the second thing that we are talking about here is saying student X was born on the 2nd of January, and then student Y is born on the 1st of January, and then student Z is born on the 3rd of January. This is why they're considered distinct items, because they are distinct. Okay, what we are assigning to x and what we are assigning to y are different. Now, the other thing is we also want all three items to be different. But within the confine of having three items that are different, we also want to kind of count all the different ways to rearrange these things so that the next one may look like this, right? 1, 3, 1, 1, 1, 2, blah, 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 right? Okay, but let's not do the blah, blah, blah. Let's think about if we just limit, okay, let's just confine ourselves to the first 3 days of an entire year. Okay, we'll just say that, okay, we have just picked these 3 days and forget about the rest of the year for now. And the question is, how many ways can we assign just these 3 specific days to 3 individuals? What would be, how do we calculate that? No, it is not 9. It is not 3 times 3, because once we use a particular date, we cannot use it again. It is without replacement. We have kind of talked about this before. So it is not 9. Okay, come on, you guys keep thinking. Keep thinking. It is without replacement where ordering is important. So what is that? Okay, I'm gonna wait until Anita is done typing. Or maybe she's not gonna type anymore. Okay, so I'm gonna confirm that Ivan is correct. It is 6. So, okay, I'm not convinced that it is actually 6. So let's figure out why it is 6. Okay, so we got 1, 3, 1, 2, and then 1, 1. This is also in F. And then the next one is going to be 1, 1. And then we got 1, 3. And then 1, 2. And then the last one is going to be 1, 2, 1, 3, and then 1, 1. Okay, so I challenge you guys to think about a different way. So Andre it's not 27. 27 is way too many because 27, sorry. 127 is 3 to the power of 3. That would work when we want to also include duplicate cases. But we are not dealing with duplicate cases because we have already selected 3 exact dates and we do not want those. We don't want repetition because of this. We're dealing with F here, which is basically saying, everybody needs to have a distinct or different birth dates. So there are only 6 ways to arrange this. Why? Because there are 3 choices for X. Okay, so X being the first one that we consider, X can choose any one of the 3 dates that we have pre-selected. But whatever X has chosen, Y cannot use that. So Y only has 2 choices left. And then once X and Y have chosen their dates, then Z has nothing left to choose from. There's only 1 date left. So it becomes 3 times 2 times 1, which is indeed 6. All right. So now we look at this and go like, so how is that going to help us? Because we're only looking at the first 3 days of the whole year, which is one way to find 3 distinct days out of 365, right? So how do we account for all of those other ways, right? Okay, so now we do an abstraction. Okay, abstraction means we lose some details so that we can think about a solution to be a more general solution, and then we apply that to something else. So don't think about January 1st, January the 2nd, and January the 3rd anymore. Think about these 3 dates as I would just say D1, D2, and D3. Okay, so now you say, oh, okay, so we have D1, D2, D3 is in F. We have D1, D3, D2 in F. Then we have D2, D1, D3 in F. And then we have D2, D3, D1 in F. And then we have D3, D1, D2 in F. And then we have D3, D2, D1 in F. Okay, so assuming that we lock down to just these three specific dates that are different, D1, D2, and D3, there are 6 ways, okay, to assign these 3 different dates to the three different students, so that we meet the requirement of why something belongs to F as a set. Okay. All right. So now the question is, how do we come up with D1, D2, and D3? In other words, we're looking at 3 different dates, and these 3 can be any 3 dates from a year as long as they are not the same. So how do we figure out that? How many ways can we choose 3 dates out of a whole year? My question answers its own question, by the way. So I'm going to let you guys think about that a little bit, and then we'll get back to this. All right. So Anita is correct. Well, partially. It is related to that permutation stuff, but it's not permutation. It is not permutation, but it relates to permutation. So what stuff are we talking about? Combinations! Exactly. Okay. So what we want to do is to basically say, how many ways can we make a set of D1, D2, D3 so that D1 is D1, D2, D3 are dates in a year, but they are different. They're distinct. Okay. That becomes the question. And before somebody says, okay, but how come these D1, D2, and D3 in a set, because we see the curly braces, but these guys are in parentheses? Why? Well, that's because we don't need to take ordering into this consideration, because if we also consider D1, D2, D3 is to be different from D2, D1, D3, then we will end up with duplicate cases. So we just want to find different ways where ordering is not important. Okay. All right, so how do we figure that out? Well, remember what I said. My question answers the question, because I used the word. Okay, which word do you think is the giveaway? It gave away the answer. Exactly, Angel. Okay, very good. Because I used the word choose. Okay, so whenever I use, well, okay, I shouldn't say that. But the word choose is associated with the number of combinations. So we are now looking at combin 365 3 is the number of ways to choose 3 distinct dates from a year. And that would be D1, D2, and D3. And then once we have that, then we'll multiply this with 6 in this case. So what is about this 6? Okay, since Anita referred to the permutation stuff, right? So let's think about this 6 as a permutation thing. It is actually related to permutation, because this is actually the permutation of starting with 3 items, and we want to choose 3 items out of those 3, where ordering is important in this case. So the 6 is coming from the permutation of 3 and 3. And then here we have the combination of choosing 3 out of 365. And these two need to be multiplied. Okay, so when we say combin 365 3 times permutation 3 3, this becomes the total number of ways for 3 people to have distinct birth dates. Cool. All right. So that seems to be quite a lot, right? And this turns out to be also the cardinality of f, because we have changed our focus. Instead of counting cases where we have at least 2 people sharing the same birth date, we're now counting the cases of no one is going to share a birth date with anyone else in class. So if we know this is f, okay, the cardinality of E is relatively easy to figure out, because the cardinality of E is the cardinality of omega minus the cardinality of f. All right. So what simplifies to 1 divided by m factorial? No, it's not going to be that small of a number. I'm not really sure to what quantity we are referring to. Let's see. No, that is not the case. So let's go ahead and revisit what is combin. Okay, so combin nm is n factorial divided by n factorial n minus m, the whole thing factorial, times m factorial. That is how we define combin. And then permutation, permut nm, is n factorial divided by n minus m factorial. Okay, so yes, Angel is correct. I stand corrected. I'm correcting myself. So Angel is indeed correct that the combination of nm is the permutation of nm divided by m factorial. That is actually correct, because we can see here that since permutation is this part here, we just have to divide an extra m factorial to get to the combination part. So very good. Good job, Angel. You're correct. Okay. So, but what are the chances, right? Because remember, we are concerned about the chances. So the first thing we want to do is, what is omega? What is the cardinality of omega? We got this one figured out already. It is really just 365, 3 to the power of 3. That's omega. So that means when you look at this entire thing, depending on how you want to simplify the equations, it becomes because omega divided by omega is just 1, so it becomes 1 minus, and then now we look at the combination of n choose m times the permutation of n. Oops, I take it back. Oh no, this part is fine. It's the permutation of no. Okay, this is. Let's deal with a concrete case and then we'll generalize. So this is a concrete case of 3 people in class. So this is 3 3, and okay, and then this whole thing divided by 365 to the power of 3. All right, that is the probability of E. This is not the cardinality of E. This is actually the probability of E. So this is the probability of E, given what we consider as our omega, or just PRE is fine, without the omega, because it's usually understood. All right. So now we want to actually see what this number looks like, right? So let's go ahead and use a spreadsheet to take a look at the actual number. All right. So calc. There we go. All right. So So we'll use a new sheet here. There we go. And we're gonna, yeah, this is just one of my own spreadsheet for my own stuff, but that's okay. So we want to just do this calculation, and we want to use a column for n. So we know that when n equals to 2, the answer is just 1 divided by 365. That one we figure out just because it's easy to kind of figure out. But when n equals to 3, then it's a little bit complicated because now it is 1 minus what we just talked about, which is combin 365 3 times permut 3 3, and then the whole thing divided by 365 to the power of 3, and then the answer is 0.0082. In other words, it's a little bit more than having 2 people sharing the same birth date in a class of only 2 people. When we have a class of 3, the chances of at least 2 people sharing the same birth date is increased, but just a little bit. Does that make sense? Kind of intuitively, does it make sense? Maybe. All right, cool. Excellent. All right, so now we go back to the equation or the formulae that we have developed up to this point and go like, can we solve a general problem now? Okay, when we look at this, to be the case when n equals to 3, can we generalize this using the same reasoning? So the answer is yes, okay, because basically what 3 is representing is really just n. So that means in general, okay, so in general, this 3 is what n is, which is the number of students in class. And same over here, because these two are exactly the same, they refer to n, and this also just refers to n. All right, so now we have a generalized equation, that applies to, okay, just tell me how many people are in class and we'll figure this out, right? Okay, so the bigger question now is, remember the case of 1? We want to kind of figure out the case of 1, and some people said it's 0 because there's only one person. I mean, there's no one to share a birthday with. So this should work when we plug in 1 in place of n, right? So let's see whether that works or not. Now, I can obviously just go to the spreadsheet and do it in the spreadsheet, but instead of doing that in the spreadsheet, let's figure out what happens when n equals to 0. And we will work it out using this equation, but without using a spreadsheet, because we should be able to figure this out without using a spreadsheet. Okay, so now we want to figure out the values. What is the number of ways of choosing 0 distinct elements out of 365 cases where ordering is not important? In other words, what is combin 365 0? And I don't want to use a spreadsheet, right? So do we know how many ways can we choose nothing out of 365 where ordering is not important? There's one way. Very good. Okay, so you guys still remember that. Okay, very good. What about this permutation of 0, 0? Okay, how many ways can I choose nothing out of nothing where ordering is important? Exactly, it's 1. Okay, so this is also 1. And what about this? What is 365 to the power of 0? That is also 1. Are we kidding? So we have 1 times 1 divided by 1, which is really just 1. And then we have, that becomes the amount that we're subtracting from 1. Oh, so that means when n equals to 0, the chances will be 0. Then you guys go like, but Tech, I thought you were trying to solve the case when n equals to 1. You are correct. You just caught me. Okay, this solves the case when n equals to 0. In other words, when I have a class of 0 because people heard about my reputation and no one choose to take my classes, the chances of at least 2 people in my class of 0, there's no one in the class, having the same birth date would be 0. That kind of makes sense, right? Because if there's no one in class, there's no way for at least 2 people to share the same birthday. That kind of makes sense. Cool. But I need to go back to answer the earlier question, which is what happens when n equals to 1, because I just solved the case when n equals to 0. So now we go back to answer the case where n equals to 1. Okay, which also should be solvable using just by hand. Okay. All right, so the first thing we do is to say, how many ways can we choose one thing out of a bag of 365 where ordering is not important? What do you think? So I have a gigantic marble, a bag of marbles, of 365 of those. And how many ways can I choose just one out of the bag where ordering is not important? So without even referring to the equation, without using a spreadsheet, I want you to be able to intuitively figure this one out. Exactly, 365. Okay. And then we get to the next part, which is permutation of 1, 1, which is basically saying I have a bag with only one item in it, and how many ways can I choose just one item out of the bag where ordering is important? Exactly. Okay, very good. What about this one? What about 365 to the power of 1? Come on, you guys are on a roll here. It says, yep, exactly. Very good. Good job. So that means we have 365 times 1, which is 365, divided by 365. 365 divided by 365 is 1. So we do end up with just 1 minus 1, which is, again, 0. Oh, okay. So it is 0 for the case when n equals to 1. So now we look at this and go like, I heard Tech has a pretty big class for CISP440 because it's a double lab type of arrangement where there are 2 labs, only 1 lecture. So I got about 60 people in that class. So, oh, sorry about that. I double click on the title bar instead of single clicking it. So let me fix that. There we go. So what about that one? So instead of just plugging in the 60, let's go ahead and do something like this. Okay, so this is 4, or better yet, express this as 1 plus whatever is in the previous row. And then now I can make this equation more general, because now I can just say this is 1 minus combine 365. The 365 part is constant because that represents the number of dates in a year, at least the way we measure it. Okay, so if you're on Mars, it will be different. If you're on Jupiter, it'll be different. If you're on Venus, it'll be different. But since we're making the assumption that we are on Earth, regardless of the size of the class, 365 works. Okay, and that would be n that we need to specify as a second parameter, and that really is just this cell over here. And then we multiply that by the permutation. And this time it is the class size and then the class size again, because that really just tells us how many, if I have chosen, a particular set of distinct dates out of 365, how many different ways can I distribute the same dates to everybody in class? That's what the permutation is representing. And now we have to remember to divide this by 365 to the power of basically number of people in class, because that is representing the cardinality of omega. Basically saying, basically it is saying without any restrictions, how many ways can we have birth dates arrangements within the class? They can be duplicates, there can be no duplicates. I don't really care. Okay, that is just 365 to the power of the number of people in class, because we are not placing any restrictions. Everybody get to pick from any one of the 365 days. All right, so now we get a much more handy way to look at all the different cases. So when we have a class of 19, we can see the chances is that's pretty high. Okay, the chances of at least two people sharing the same birth date is basically 38% when we have a class of 19 people. So when we get to 23, it's about half and half already. So when we have a class of 23 people, then the chances of at least two people sharing the same birth date is 1/2. That is actually pretty high. If you think about it, this is higher than what we normally would perceive. So now we're going to extend this all the way to 60, because I said, let's find out the chances for my kind of bigger class with 60 people in it. So when we get to 60, which is this one here, we can see the chances of at least two people sharing the same birth date is 99.4%. That is pretty high, which basically it says, we almost know for sure, okay, almost for sure, that at least two people within that class share the same birth date. Isn't that cool? I mean, isn't that kind of not what you would expect? Angel is typing something. We'll go ahead and wait. Yes, being lucky and unlucky, those are all probabilities, right? Those are all probabilities. But this is really interesting, because if you plot this, okay, we can go ahead and do that. And before I do that, let me insert two more rows to take care of 0 and 1, and then we'll go ahead and do this. Okay, so we have 0, and then we can extend this all the way up to here, and then this can be copied to here. No, that doesn't make sense. That does not make sense. Oh, because those are still constants. Okay, never mind. There we go. Okay. So now we have and then this is the probability. And when we have something like this, we can just go ahead and select the cells, and then we go to Insert, and we want a chart. Insert, chart, second item. And we want to use a column graph by, yeah, I guess your column is fine. And we just click Finish. No. That cannot be the case. That's not what I want. Because I want a plot, we want an XY chart, not a frequency chart like this. Okay, so let me get rid of this. Yes, I would have failed a spreadsheet class. Alright, let's do it one more time. Now I want to do this because, I think when you look at the shape of the graph, you might be surprised. Okay, so we go back to Insert Chart, and we want an XY chart this time. And then we click Finish. That is what the chart looks like. So the horizontal axis is the number of people in class, and then the vertical axis is the probability. We can see how initially, it does not increase. It's a sublinear increase, and then at some point it becomes sort of linear, and then it increases rather rapidly, and then it approaches 1 once we get past a certain point. And when we get to 365, when the class has exactly 366 people, then we know the chance is going to be 1. Okay, there's no way that no one in class shared the same birth date. So that's kind of interesting, okay? Because most people know that when you have a class of 366, then the chances becomes 1 exactly, because hey, we only got 365 days in the year. When there are 366 students in the class, then at least 2 people would have to share the same birth date. That makes perfect sense, okay? Intuitively it makes sense. But what is not intuitive is how we get close to 1, even when the class size is 50 or so. It is already pretty close to 1. And it basically just stays very, very close to 1 until we get to 366. That is interesting. All right. Is luck just the derivative of an event v with the highest value? I do not know. I don't know how to quantify luck, because that's basically just probability, but we are associating a probability with a construct, of luck, which has to do with a judgment of what is good and what is bad, what is right and what is wrong, that sort of stuff. But in probability, calculations, there's no such thing as luck or unlucky, because we are really just looking at probability. All right. So that is the birth date problem. I'm looking at the time. We got about 15 minutes left. And this is just the kind of the same explanation that I got. And now we are moving on to section 4. Ivan is still typing, so I'm gonna wait until he's done typing, and then we'll get to section 4, which is also very interesting. That is correct. The actual distribution of birth dates may not be even. That is correct. It also depends on the kind of animal too, because certain animals only have gestation, in certain seasons of the year, such as sheeps. Okay, sheeps do not carry babies, in the winter. Assuming, well, humans or rats or mice, these mammals tend to be able to conceive and carry babies all year round. Yes, we do have similarities. Yep, and the birthday distribution can also be studied, because the census and all kinds of government agencies, they have birth date information of individuals, so we know the distribution. You can even probably just look up, by Googling. So if you Google birth date distribution or something like that, you'll probably find graphs and studies and stuff like that. Cool. So now we're going to move on to section 4 that talks about when we basically toss a coin, what are the chances of blah blah blah. Okay, so in this case I'm using a very concrete example. If I toss a coin exactly 5 times, what are the chances that there are 3 heads and 2 tails out of the 5 tosses? So in this case, ordering is not important, so I can have head, tail, head, which is interleaving all the heads with tails, or I can have head, head, tail, tail, or I can have tail, tail, head, head. In other words, I don't really care about the ordering, as long as I end up with 3 out of the 5 tosses landing on the heads, it counts as my event. Okay. So now we want to look at the probability. Okay, what are the chances? First thing we do is once again looking at omega. So in this case, omega is pretty easy to understand because we are tossing a coin exactly 5 times, and then each time we toss a coin there are 2 possible outcomes, which is either head or tail. So that means the cardinality of omega for this very specific case would be 2 to the power of 5. which is exactly what, 32, right? Okay, so the cardinality of omega is just 32. So now we have to think about E, which is the event, which is a subset of omega that we are interested in, which in this case would be basically stuff that can get past a filter of, okay, let's count the number of heads and tails. If there are 3 heads and 2 tails, it passes the filter. Okay. So in that case, how do we know, the cardinality of E in this case? So this requires kind of a way. Once again, this is all about how we look at something. Okay, so this has to do with how we look at something. Because if we look at something like this, okay, then it gets a little bit harder to associate it with things that we have already understood. Because we are looking at 5 tuples, where each item in the tuple is either a head or a tail, but we want to count the number of heads and tails in a tuple. And we never really talked about, formal ways, of how to treat the counting of something inside a tuple. That's not something that we have talked about. So instead of doing that, okay, we can think of the problem in a different way. So as an example, which is illustrated here, we are going to encode. Okay, it's a problem of encoding. Okay, how do you represent something, and not to lose any information, but in a way that is easier to process because it relates to something that we have already talked about. Okay, so it has to do with reframing something into something that we are familiar with. So when we look at a particular sequence of heads and tails, in this case it is head, head, tail, tail, head, we can now represent it as a set. Now this is not a typo, these are actually curly braces. In other words, 0, 1, 4 are elements in a set. I don't see anything that relates this 5 tuple to this particular set of 3. Well, we are using, okay, so the explanation here first clarifies that we are using zero-oriented indexing. So what this set here is indexing the items in a particular tuple, and we're only indexing the ones that we are quote-unquote interested in, which in this case would be the heads. Okay, so we're not counting the tails. We just want to know what are the indexes to the heads inside this particular 5 tuple. That turns out to be index 0, which is this particular head, index 1, which is this particular head, and then index 4, which is this particular head here. Okay, then people would be asking, it's like, okay, so now I can see, how we are encoding the same information. Okay, head, head, tail, tail, head as a 5 tuple can now be encoded as a set of 0, 1, 4 as elements in the set. And how is that going to help me, right? How is that going to help me? Well, the way it is going to help you is because now we think about 0, 1, 4 and go like, well, we kind of learned that sets are related to combinations, where tuples are related to permutations, because one is where ordering is not important, which is a set, and one is for cases where ordering is important, which is a tuple. So in this case, it is a set. So we think about, okay, well, does it have anything to do with combinations? Okay, if so, what are we talking about combinations? So now we think about you having a bag. Okay, so once again we have a bag of marbles, but these marbles are labeled from 0 to 4. 0, 1, 2, 3, 4. And what we are trying to do is to figure out the number of ways to pick 3 marbles out of the bag without replacement, where the ordering is not important. Okay. Oh, so that really is just combin. Okay, we are counting combinations, where we have 5 items to in the bag, and we're choosing 3 items out of the bag, where ordering is not important. So it's 5 to choose 3. Oh, okay, so now that we know how to figure out the cardinality of E, which is just 5 choose 3, the probability of E, the event set, it's just really going to be the cardinality of E divided by the cardinality of omega, which in this case is 5 choose 3 divided by 2 to the power of 5. Aha. Okay. So let me just kind of highlight which part we are talking about here. So I'm really only referring to this part at this point. Are there any questions about how we figure out the probability of a coin landing 3 times on the head out of 5 tosses? Okay, I'm not seeing any new traffic. No, there are no probability stuff in the exam because we are going to stop with propositional logic. So the exam only has material since after the first exam. It will include and up to propositional logic. All right. So getting back to this, okay, so now we want to kind of use the spreadsheet to help us visualize stuff, right? Because a spreadsheet is really good for that sort of thing. So we'll use a new spreadsheet, and so how many coins, how many tosses do you guys want to work with? Because I kind of have to fix the number of coin tosses first before I can plot this in the curve. Try to pick a larger number, like 20 maybe. Is that okay? Okay. So we have exactly 20 coin tosses, and now we want to just look at the cases where the number of heads is, it can be 0, right? There's a chance that all 20 tosses would land on the tail, so we end up with 0 in this case. And now we want to figure out the probability, which is something that we have already worked with. So that's my smoke alarm, beeping in the background. So now we just plug in the equation. No, not yet. It's all right. It's because I have a, how is it called? Air fryer. That's it. Okay, so I got an air fryer, and air fryers are very, very good. They're I really like it a lot. Except it also smokes a lot. Depending on what you're air frying, it can smoke a lot, and then you just end up having you end up with a drill, a fire drill, and a test of your smoke detector. I'll just put it that way. All right, so getting back to this one. So the com bin is going to be referring to this 20 because this is where we're choosing from. We have 20 different tosses, and we are trying to figure out how many ways can we have 0 heads out of the 20 tosses. So I'm going to refer to the 20 as let's see, $1. The dollar is necessary here so that it doesn't change as I copy the formula from one cell to another cell. And then the other one is going to be 0 because that's referring to the number of heads, right? So now we divide it by the power of 2 to basically the same thing, which is 20. So once again, I refer to that as $1. A is the column number, 1 is the row number. That's how you designate a particular cell in the spreadsheet. So press the enter key, and we go like, oh, it's a pretty small chance. That kind of makes sense, right? Because if you want like out of 20 coin tosses and you want every single one to be a tail, to land on the tail, you can kind of imagine the chances pretty small. Okay, but now I can copy and paste, or just, oh, I cannot yet do it because I have to refer to this one as 1 plus the previous item, and this one I can just replicate because it has the correct references already. So now we can do a copy and paste. And since I'm starting on cell 3, we'll end with cell 22 or row 22. Then we'll have all of the rows that we need. There we go. Oh, okay, I miscalculated by 1 because there's also the case of you have 20 different tosses and we have exactly 20 heads out of the 20 tosses. Okay, So the first thing we want to do is to visually look at the numbers, okay? And go like, do we notice anything kind of interesting about these numbers? And probably most of you will recognize and go like, hey, this looks exactly like this. And the second item looks exactly like the second item to the bottom, and so on. And you're right. That has to do with we are assuming a coin that is even, not loaded, which means the chances of landing on the head normally is 0.5, and the chances of landing on the tail is exactly the same. And that's why you can see there's a symmetry, of the first and the last item, and so on. But I think the more important part is to look at the shape of this particular plot. Okay, so I'm going to do the same thing over here. Select the cells, insert chart, and this time we also want to look at an XY chart. Okay, so it's a scatter chart, and we can say, let's see, lines only, because I want to emphasize on the shape that it's going to draw. And yeah, sure, go ahead and smooth out the lines, and we'll finish. It'll go like, I remember seeing this in one of my other classes. And what would be that class? In which class have you seen a distribution? Okay, damn it. I just I just blurted out the answer. ET335. I have not taken that class. I'm not sure what that class is about. Okay, a confidence chart, which is based on a normal curve, right? It's based on distribution of a normal curve. It is from statistics. Very good. Okay. That is interesting. But we also know in statistics, if you integrate the area under the normal curve, what do you get? What is the integration of the area under a normal curve in statistics? What do you normally get? No. Not biology. Come on. It's the summation of everything that is possible. It's the summation of the probability of everything that is possible. What should it sum up to? Exactly. It is 1. So let's see whether that works here. Okay, so we are now summing all of these things and see whether it is going to be 1. It is exactly 1. Cool. Okay. So we are out of time today. I would like you guys to study for the exam first on Wednesday. But, if you have time, and, because I won't be talking to you on Wednesday. So if you have time, you also want to kind of continue to read the rest, because things get much more interesting, okay? Because, when we look at a curve like this, it's like, okay, everything is kind of mathematical, kind of, we can see stuff, we can see the shape, and everything seems to be intuitive. And then at some point, text starts to throw out things like this. Okay, it's like, okay, we have some theorem proving here, and then we start to talk about proof by induction, and then we start to look at things that are even uglier, like this. Okay, and then we talk about binomial distribution. Then we go like, okay, fine. How does any of this have anything to do with computer science, right? So we'll get to those. Okay, we'll get to those hopefully on Monday next week, because we have Wednesday being our second exam. So we'll get to Monday next week and we'll start to make all the connections. Okay, and I will also emphasize on the application of all of this stuff here, because if you don't know there's an application of all of this stuff here, you're going to forget very quickly about all of this stuff. Let's see. I'm just catching up on the text channel. I'm not taking row today. I like that equation. Interesting equals difficult. It's more like interesting to one person can be difficult for another person. No, I already answered the question of no probability material on the exam. Yes. Okay, so I think we got everything addressed in the question, and my smoke alarm is not beeping anymore, so that's good too. That is true, Tom. Absolutely. Difficult does not always equals interesting. Absolutely. Yep. Okay, so I will let you guys go, and I will go eat whatever is causing the smoke alarm to go off earlier. All right. Well, thank you. I will finish grading hopefully today. I got the spreadsheet almost all filled up, but as I said, I had to go back to regrade. I would say about 10 of those because I discovered someone was being smart with one of the format of the questions, but not reading the entire question. So I have to go back and regrade some of those things. Okay, cool. I am going to let you guys go. Have a nice day, and I'll see you on Wednesday in the second exam.